Thank you for attending this presentation. My name is Singh, and today I will be presenting on the nonlinear dynamic analysis of a shape-changing finger-like mechanism for morphing wings. This project was done at the Nonlinear Mechanics and Dynamics Research Institute hosted by Singh National Laboratories and the University of New Mexico, and done in conjunction with Kayla Wielgus of University of Washington, Robert Kuether of Singh National Laboratories, Ignazio of the Italian Aerospace Research Center, and Professor Matt Allen of the University of Wisconsin-Madison. This is a view familiar to many of us if we've been lucky enough to sit on the window seat of an airplane. Here we see control surfaces, in this case flaps, that can drastically affect aerodynamic performance for different phases of flight. However, it's important to note that these are actually a compromise between generating lift as well as the weight of the wing. So research has been put into understanding this compromise and seeing if we can go past it. Well, the best way to learn is to learn from our best flyers, aka birds. Birds naturally have this flexible variable camber wing, and we can translate that into this idea of a variable camber mission adaptive wing, in this case shown for the F-11 aircraft. This variable camber wings allow the camber to change for different environments such as gliding, diving, or other maneuvering, and hence can be translated through morphing wings. However, these are not just a concept, these actually exist. They are flexible, shape-changing, and bio-inspired high-lift devices that can 1. Reduce fuel consumption and also reduce airframe noise. It can be done in one of two ways currently, either a kinematic system or a compliant system. For the purposes of this presentation, we will be focusing on kinematic finger-like mechanisms for morphing wings, specifically designed by the Italian Aerospace Research Center. These finger-like mechanisms consist of different blocks of ribs, shown as B0, B1, B2, and B3 on the figure on our left, that are connected by hinges and links that move by load-bearing actuators. We can see this movement on the figure on our right. However, as soon as we start introducing several connected components, these begin to exhibit frictional nonlinearity at the interfaces. This in turn can affect the response of our wing structure. So even if we tighten these bolts, tighten these connections as much as we can, they will still exhibit regions of slip at the edges of contact that can be either described as micro slip or small scale slip at the extremities, or macro slip, a global slipping behavior. These in turn introduce hysteresis and this amplitude dependent behavior that can be characterized by traditionally a decrease in frequency with respect to amplitude and an increase in damping with respect to amplitude. To model this nonlinearity, we will look to utilize the quasi-static modal analysis framework. This is proven capable and useful for predicting the nonlinearity in simple structures, but we will be extending this to different types of bolts in a much larger structure. At first, we must do a nonlinear preload analysis where we try to connect all of our connections. Secondly, we will do a linearized modal analysis to determine the modes of vibration about our preloaded state. And finally, we will apply a modal force in the shape of our mode of interest to see the amplitude dependency and how that affects the joints in our structure. For QSMA, we will force the structure, generate our quasi-static portocycle response, and use Mason's rule to generate our full cycle to get this amplitude-dependent behavior. So as mentioned, QSMA has been successfully done on these smaller scale structures with fewer joints and primarily bolted connections. So then the question arises, can QSMA be successfully applied to this industrial relevant structure? To do so, we have our finite element model on our left, and if we explode that for various connections, we can see that it has hundreds of different connections that are very different. So we have these pinned connections, we have bolted joints, we also have these different shoulder joints that all exhibit frictional nonlinearity differently. So the goal of this work is to predict the nonlinear response of a key mode of interest for the morphing wing model. So for the first step of our QSMA approach, we will apply a preload using a point load on the tip of the wing to simulate laboratory test conditions. On our figure on our bottom left, we have the tip load preload force, and then we have the tip response during this preload step. And we see a potential problem. We see this jump in displacement with the increase in load. If we look prior to that jump, we have a stress state on this single link with minimal stress. However, after that jump, we have considerable stress built up on this linkage and potentially other linkages as well. This buckling behavior of the linkage is thought to be an artifact of the model. The finite element model may not be refined enough along these hinge joints and other contact regions, which could lead to artifacts such as facet locking when rotating about a hinge joint. To mitigate this, the finite element model would need to be refined near these joints to potentially see any benefit. However, one can expect to expend considerable resources in time and effort for mesh refinement and see an increase in computational costs to predict this stick-slip behavior, and even a fine mesh may be far from adequate. Given the time constraints, we were not able to increase the mesh density, so we decided to proceed with the linearization about the preloaded state and run modal analysis and QSMA just to see how this process fares for such a large structure. We were able to obtain a mode shape for our mode of interest as shown here at 166.1 Hertz. So we were then able to excite our structure in the shape of that mode to generate our nonlinear frequency and damping curves with respect to amplitude. Here we see these curves here for two case studies for two various ranges of tip displacement. And we immediately notice that neither of these curves approach our linearized frequency at around 166 Hertz. That indicates that we are in the macroslip regime, and if we lower our prescribed tip displacement load for QSMA, we could potentially be in the microslip regime. However, we were unable to obtain converged results for lower force amplitudes, where we presumed that the microslip behavior of the structure would be observed. So the green line is our assumed response, not actually calculated, based on what we see specifically for our macroslip QSMA behavior. To evaluate the accuracy of QSMA on this model, we will compute a static hysteresis loop and compare that against that generated from QSMA. QSMA uses Masing's rule to recreate 1 1/4 cycle from a quarter cycle vibration. So the quarter cycle is shown in orange as the quasi-static response, and the full hysteresis loop shown in blue is generated through Masing's rule based on symmetry. We will try to recreate this behavior statically by discretizing the loading on the structure such that it goes from 0 to a particular alpha, down to negative alpha, and back up to alpha to close our static loop. And we can see the result of that on the figure on our right, where red is our quarter cycle QSMA, blue is that estimated from Masing's rule, and orange is our direct statically loaded cycle. We see two things here. One, where that direct cycle does not overlay with QSMA, and there could be plenty of reasons, including facet locking and issues with the final element model. And two, that this quarter cycle, or the direct cycle, has not been completely closed. An alternative to this full order model is to look at a reduced order model just to see a little bit more about what's going on. So to do so, we construct a reduced order model by reducing an entire interface, as shown here, into a singular point using multi-point constraints, and connect these 2 points, for example, for this rib and this washer, through a joint model where it could be linear springs or a nonlinear hysteretic model. For the reduced order model, we join these components together using linear springs. However, in this case, we allow the linear spring in the rotation of the x direction, as in the bending of the structure, to vary, and then calculate the modes about those states. This is done to see the behavior of the structure in macroslip as the stiffness of that joint goes to 0. And we can see the results of that in our figure on our left, where when the stiffness approaches 0, we see a significant reduction in the natural frequency. It's important to note that this model has not been tuned yet to the actual frequencies. This is primarily only to show the trend. And we can see that this is similar to what we see for QSMA for our full order model, hence potentially indicating that we are already in macro slip. To conclude, we applied this QSMA framework on this industrial scale structure, and we applied a representative tip load as a preload to obtain contact on a very coarsely meshed interfaces. We also generated this quasi-static frequency and damping curves that seem to show this macro slip behavior. It's important to note that QSMA has typically been applied to bolted connections, which have had much higher preloads and mainly on flat-on-flat interfaces rather than this pinhole hinged frictional contact in this model. Although we did not see very accurate results, this work is a step forward towards high fidelity nonlinear finite element modeling for these types of structures. These models are key for successful virtual testing demonstrations, and they pose several challenges, which we have already seen, that must be overcome to make advancements, responses, predictions with confidence. For future work, it suggested that we refine the meshes at the interfaces to eliminate facet locking and to see if we can remove this observed jump in displacement. Furthermore, it would be a good idea to calibrate the reduced order model given more time to match the linear frequencies about the preloaded state. Once we have an accurate linear model, then we can apply nonlinear hysteretic elements and update to match the full order quasi-static frequency and damping curves, given that we can obtain those using QSMA on such a large structure after eliminating facet locking. Furthermore, this is only one part of this morphing wing. To fully model it, we must add a hyperelastic compliant skin along the rib for a more realistic model, which will introduce significant stiffness. Furthermore, this is only a small portion that we're looking at. We're only looking at multi-point constraint reduction. It's important to gauge additional reduction techniques on this industrial scale model. With that, I'd like to acknowledge that this work was done at the 2020 Nonlinear Mechanics and Dynamics Research Institute, hosted by Singh National Laboratories and the University of New Mexico. I'd like to thank you for listening and open it up to any questions.